Hello everyone. So today we are going to discuss about the process referred as Hall-Héroult process. Okay, so let's start with Hall-Héroult process. Now the very first thing, this process is used for the extraction of aluminium from alumina. Okay, alumina is a ore of aluminium from which we will extract aluminium, and we will extract the aluminium using Hall-Héroult process. Okay, now Hall-Héroult process, it starts with firstly purification of bauxite. Okay, now what do you mean by bauxite? Let's understand. So you first have a ore which is referred as bauxite, and bauxite is nothing but impure alumina. Okay, so whenever you have impure alumina, that would be referred as bauxite. Okay, so let's go further. Let's move ahead with the next part. Now, talking about the ore bauxite, this ore bauxite contains 75% of alumina, that is Al₂O₃, and it contains 25% of other impurities. Okay, now what are the impurities present in alumina? The impurities that are present in alumina, so the impurities that you have is majorly of sand and iron 3 oxide. Iron 3 oxide, that is nothing but Fe2O3. Okay, so these are the major impurities that are present in alumina. Okay, and that takes up around 25% of the entire alumina or the entire bauxite that you are using. Okay, now before we move ahead, I just need to point out few major things over here. If you have impure bauxite, please remember this. Okay, if you have impure bauxite, or let me put it in this way. Let's suppose if you have impure alumina, that is you have Al₂O₃, okay, with impurities. So if you have impure Al₂O₃, this is referred as bauxite, which is the ore that we get from the earth crust. Okay, but then when we purify this Al₂O₃, this pure Al₂O₃, let me write it over here, this pure Al₂O₃ is referred as alumina, and this alumina would be something that we are using for the extraction of aluminium. Okay, now understand, before we move ahead, I just want to put down one more thing for you. Okay, how do you convert this bauxite, which is impure Al₂O₃, into pure Al₂O₃? Now you don't have this, but then just to appreciate the process, we are doing this. Okay, nothing more than that. You don't have this for your IGCSE exams. Okay, if it comes as a hot questions, you're sorted. If it doesn't come, absolutely fine, not a problem, but then you're just doing it for the sake of appreciation of the process. Okay, now what happens is, in the first step, okay, I take impure Al₂O₃, which is referred as bauxite, and to this I add NaOH. I'm giving you the balance reaction directly. So I add 2 NaOH. What do I get is, I get 2 NaAlO2, and along with this I get H2O. Okay, now this NaAlO2, what is this referred as? This is referred as sodium aluminate. So over here I get sodium aluminate. Okay, this is NaAlO2, and this Al₂O₃ that I'm using is impure, and therefore this would be referred as bauxite. Please remember this. Okay, now further what happens is, let me just insert few spaces over here. Okay, now what happens is, you have NaAlO2, that is sodium aluminate. This sodium aluminate is now converted into AlOH thrice, that is aluminium hydroxide. How is it done? So we have the second step over here, that is NaAlO2. Okay, this reacts with 2H2O to give AlOH thrice plus NaOH. Okay, and AlOH thrice, as we all know, it is aluminium hydroxide. Now this aluminium hydroxide, that is AlOH thrice, when this aluminium hydroxide is heated, okay, what you would get is you would get Al₂O₃ plus you will get 3H2O. And this Al₂O₃, because now it is pure Al₂O₃, this is referred as pure alumina, and from this pure alumina we would extract aluminium. Okay, now let's move on with the next part of the story. So till now we have discussed about how pure alumina is obtained. Okay, in your textbook it has just said that pure alumina is obtained by adding Al₂O₃ or adding bauxite in NaOH. We can simply remember that. Okay, but then I have told you this entire thing in the green box over here just for the sake of appreciation of the process, so at least you know what exactly is happening. Okay, let's move further. You don't, again I'm repeating, you don't need to remember this, but then if you know it, it's absolutely a win-win situation. Further, let's see. Now there are few problems when I come to extraction of aluminium from alumina. What is the first problem? The first and the most major problem over here is that Al₂O₃ has a very high melting point, absolutely high melting point of around 2050, okay, or 2030, my bad, 2030 degree Celsius. This is absolutely very high melting point. Okay, further, Al₂O₃, aluminium, is highly reactive metal, and because it is highly reactive metal, I can't just remove oxygen by using a normal reducing agent, and therefore I have to go for a process of electrolysis. That means I need to break the molecule with the help of electricity. Now understand, because I need to break the molecule with the help of electricity, I need Al₂O₃ in liquid form or in molten state, but because Al₂O₃ has a superbly high melting point, that is 2030 degrees Celsius, it's very difficult to melt it. Okay, so that's the very first and foremost, you could say, drawback, or you could say a problem which is occurring in the process. Okay, so how do we tackle this problem? We tackle this problem by adding something very, very important into it, and we add another ore of aluminium, and that ore is referred as cryolite. Let me rewrite it for you. Okay, so that ore is referred as cryolite. Okay, and cryolite, the formula of this compound is Na3Al(F6). Okay, this is another ore of aluminium which is used in the process of extraction of aluminium. Now, what is a feature or what is a added advantage by using cryolite? What happens? The first and the foremost advantage is that the melting point reduces to 900 to 1000 degrees Celsius. See, you could see a pretty large jump over here, right? So therefore, what you can say, the melting point has reduced from 2030 to merely around 1000 to 900 degrees Celsius. Okay, the second most important thing is this acts as a solvent. Okay, cryolite acts as a solvent for Al₂O₃. Okay, and the third and the foremost is because you're using a low temperature, that's the reason you're saving on energy, and because you're saving on energy, obviously this is a energy and cost saving method. Okay, because energy is stored, obviously you need not put more amount of money into it, and therefore even your cost of making aluminium is reduced. Okay, so these all are the advantages of using cryolite. Further, now if I talk about cryolite, or if I talk about extraction of aluminium from Al₂O₃, Al₂O₃ in presence of cryolite, okay, I use something like this. Okay, I use a, you can say a assembly, something like this. Okay, and this is referred as Hall-Héroult cell. Now if you look closely at this cell, let me write it in the figure for you. Okay, if you look closely at this cell, then I have a negative terminal over here. Sorry. Okay, so yes, I have a negative terminal over here, a positive terminal over here. Okay, now what do you mean by negative and positive? Anode and cathode. Who is anode, who is cathode over here? So we know that during electrolysis, anode is always a positively charged terminal. So therefore this positively charged terminal becomes the anode and the negatively charged terminal becomes the cathode. Okay, the next thing that I need to understand. Okay, the anode is made up of graphite electrodes. So the anode is actually the electrodes, whereas the cathode is a carbon casing which is placed at the bottom of the cell, or at the bottom of this vessel. Okay, now in this vessel, what I'm adding two different things. Let me just put down another color for you. Okay, so in this we are adding two different things. The first one is aluminium oxide and the second one is cryolite. Again, as we discussed earlier, the melting point is between 900 to 1000 degree Celsius, and because I need to maintain a huge amount of heat over here, with the help of electricity, I would be using a very small voltage of 5 volts. So I'm using a voltage of around 5 volts and a current which should be a very high current of around 200 kilo amperes. Okay, so let me just write it over here for you. So the voltage that I'm using is pretty low, that is around 5 volts. Okay, and the current that I'm using is very high, which is around 200 kiloamps. Okay, so this is all the things that I need to go forward with. Now talking about once again anode and cathode. Anode is positively charged, cathode is negatively charged. Okay, let's see what happens further into this. So let's dive down into the actual reactions. Okay, so anode, do you know it is positively charged? The answer is yes. So anode being positively charged. See, now if I talk about Al₂O₃, okay, I have two elements that would be obviously coming into picture. The first element is the aluminium, that is in +3 oxidation state, and oxygen in -2 oxidation state. Okay, so over here now let's understand what happens. So if I talk about Al₂O₃, and in this if I'm talking about two different elements, that is aluminium and oxygen, definitely Al +3 being positive will get attracted towards the negative terminal, that is the cathode, whereas oxygen O-2 being negative will get attracted towards the positive terminal, that is nothing but your anode. And as we all know, what happens at cathode reduction takes place, and what happens at anode, then at anode oxidation takes place. Okay, so let's try to understand the reactions, what would actually happen at the anode and what would actually happen at the cathode. So let's talk first about the anode. Now at anode okay, at anode, who is getting attracted? Obviously it's O-2. So what would happen at anode? Oxidation happens. Oxidation is nothing but the loss of electrons. So even I'll write it down for here, loss of electrons. So what is going to happen? You would have 2O-2 gets converted into O2 plus 4 electrons. I have written the reaction directly. Is it fine? Or we'll do one thing. I'll first write down the basic reaction and then I'll write down the main reaction finally. Okay, so what actually happens at anode? At anode, you would have O minus 2 gets converted to oxygen plus 2 electrons. Now, again, oxygen single atom, is it stable? The answer is no, it's not stable. So therefore, what would happen is I would require one more atom of oxygen. So I would have 2O minus 2 gets converted to O2 and 4 electrons over here. So I hope now the reaction is clear. Let me write this reaction once again neatly for you. So what would be the final reaction? You would have O minus 2 gets converted into O2, obviously gaseous, plus you would have 4 electrons that would be liberated at the anode. Now, similarly, let's understand what happens at the cathode. So, at cathode, we know reduction takes place, and reduction is nothing but what? Reduction is nothing but gain of electrons, right? Oxidation is the loss of electrons, so reduction is the gain of electrons. So now cathode being negative, obviously who is going to get attracted? It's the aluminium that is going to get attracted. What would happen? So Al3 plus will gain 3 electrons and finally get converted into Al solid. Okay, now obviously this Al won't be in solid state, it has to be in the molten state. Why? Because we are continuously heating the entire reactor, we are continuously heating the entire cell. Okay, and therefore if you could see in the diagram over here, you could actually see a siphonating column from which liquid aluminum is continuously extracted out of the cell. Okay, so let's not bother about it so much. You would get aluminium at the cathode. Okay, now one important thing that happens, understand, I'll just write it in the diagram itself so that it becomes clear for you to understand. Okay, so now one important thing that happens over here, listen, over here we know that at anode oxygen gas is getting liberated. Am I right? Okay, now oxygen gas is getting liberated, that too at graphite electrodes. So wherever you have graphite electrodes, oxygen gas is getting liberated, and you are doing this reaction at a very high temperature of around 950 degrees Celsius. So what happens is the graphite, which is made up of carbon, this carbon rod or this carbon in the graphite rod starts reacting with the oxygen to give you CO2. Okay, and because it starts reacting with oxygen, it gets eroded after some time. Okay, who gets eroded? The electrodes get eroded after some time, and that's the reason they need to be replaced periodically. Okay, so that's pretty much about Hall-Héroult's process. Okay, I guess we have cleared out all the major points that would come in Hall-Héroult's process. The first and foremost important point is what is the use of cryolite, the most important thing over here. Okay, then they might ask you, okay, what is pure aluminium, what is pure alumina, what is impure alumina? So impure alumina is called bauxite, pure alumina is called as aluminium or alumina. Okay, then yeah, that's pretty much it. They might ask you what is the formula of cryolite. So we have written it over here. The formula of cryolite is Na3Al(F6). Okay, I've also mentioned keyword as a keyword over here. So cryolite, we are using Na3Al(F6) because, so you'll just read this out. Sodium aluminium fluoride, that is Na3Al(F6), and ore of aluminium is used in extraction of aluminium to lower the operating temperature of the electrolytic cell, now replaced by synthetic sodium aluminum fluoride produced from common mineral fluoride. We don't need to bother about this. Okay, no one is going to ask you in that detail about cryolite. So I hope Hall-Héroult's process is clear to you. We'll meet in the next part with some more points to discuss about some other processes or about some different topics. Till then,